speaking here first.
Sorry, and it's 45 minutes.
Yeah, so it's informal, so you can interrupt, you can do whatever you want. Don't worry about that.
Well, thank you very much, Nathan, and everyone else for a very hospitable few days here. Now, I'm not sure what the expertise of the audience is, so I'm assuming that you're not, well, I'm not going to assume that you are experts in string theory. However, it's very difficult to give a talk on string theory without being a little bit technical, but I'm going to do my best. So the subject I'm going to talk about is an aspect of string theory that I worked on for some time, which has to do with the structure of the theory if you expand it at low energies, a low energy expansion, which is the extension of Einstein's theory. The lowest term in the low energy expansion of string theory is the Einstein theory, of course, and the theories which are easiest to talk about, or the ones where one can be most precise, are supersymmetry, have a high degree of supersymmetry. So the lowest order term in the low energy expansion is a supersymmetric version of Einstein's theory. And the reason for looking at this is partly because it's very interesting to look at the structure of string theory and see how it differs, goes beyond Einstein's theory, and also because there's a fantastic wealth of mathematics that is contained within the structure of this low energy expansion. And also that mathematics contains the symmetries, describes the symmetries of the theory in a way which puts together, for example, perturbative and non-perturbative aspects of the theory in a very elegant and beautiful way. So I thought what I would do is begin this talk by summarizing what's known. I mean, it's a very brief summary of a subject which is quite large by now. But for this audience, at least on this occasion, that seems to be a good introduction to the second part, which is going to review some, again, this will be very sketchy, recent work that I've been involved with in collaboration with a bunch of people who have been working in this particular area for some time and have produced some beautiful results. And I and Kong-Kao Wen, the last author, have joined them for a paper we wrote recently. And there the idea is to see whether one can derive the expansion of string theory that I'm going to talk about in the first part of the talk, starting with the Yang-Mills theory in 4 dimensions and using the holographic connection between Yang-Mills and string theory, and to see how much detail one can get out. And perhaps, I mean, optimistically, that would define aspects of string theory that we can't see directly from the string calculations. So, and apologies to people who've heard much of the first part of this talk before, but I'm assuming that won't be many of you. Sorry, in the second part of the talk, I'll be making contact between Yang-Mills and string theory using the holographic connection, and in particular, the main emphasis in this recent work has been the fact that there is a image of the non-perturbative duality that is known to be a property of Yang-Mills theory. That's this SL2Z Montanon-Olive duality that was suggested in the late 70s, and the SL2Z duality of the string theory, which is meant to be, the type 2B string theory is the holographic image of this Yang-Mills theory. And it's possible, and what we've tried to do is make a very precise mapping between the SL2Z properties of the Yang-Mills theory and of the string theory. So I'm going to start by just reviewing some very straightforward aspects of the low energy expansion. So, for example, you start with the string version of the Einstein-Hilbert action, which looks like, well, it's in 10 dimensions. It's got this factor here, which is a dilaton factor. So there's a scalar field in addition to the graviton. And then, of course, there are many other fields in the supersymmetric version, which I'm not writing down. Alpha prime is the length scale, or the square of the string length, and the scalar field is related, when it's constant, to the string coupling constant. So G will be the string coupling constant, which is the inverse of, oh, sorry, which is the exponential of the scalar field, e to the phi. Later on, I'm going to use this dictionary, which translates between Yang-Mills theory in 4 dimensions and string theory in 10 dimensions. And that's the ADS CFT dictionary, which in this case relates the Yang-Mills, sorry, the Yang-Mills coupling constant to the string coupling constant. It's basically the string coupling constant is the square of the Yang-Mills, divided by 4 pi. And then the string length in units of the scale of the ADS. So this relates string theory in ADS 5 cross S5, anti-de Sitter space times a sphere, and the scale of the sphere, or the anti-de Sitter space, is L, and the length scale of the string, alpha prime, is related, the ratio, the dimensionless ratio is 1 over Gn. So this relates n, where n is the n of SUN, and the Yang-Mills coupling constant to the string scale and the string coupling constant. And if you do that, simply substitute that in this expression here, you find that this leading term is order n squared. But there are higher order terms. This is an expansion in powers of alpha prime. So this first term is 1 over alpha prime to the 4th. The next term in the theories I'm talking about is of order r to the 4th. So r is the Riemann curvature. There are 3 extra powers of Riemann curvature here, which means that there are 6 extra derivatives. Since alpha prime is the square of a length, that means there are 3 powers of alpha prime more here. So this term is of power 1 over alpha prime. What I'm going to do is transform to the Einstein frame. There's a dilaton factor that enters in the metric when you transform from this string frame, where string theory is defined, to the Einstein frame, that you pick up an extra factor of a power of the coupling constant. And then in general, there are moduli, scalar fields, and there's a scalar field dependence multiplying this r to the 4th. This will be very important in my talk, and that's a generic feature, that these higher derivative terms have coefficients which are functions of scalar fields or moduli, and understanding those functions is what a lot of this talk will be about. If I do the same thing as I did before, and I transform this, use the dictionary to go back to what this should look like in Yang-Mills theory, then here's a more general. This is the lowest order correction, and these are higher order corrections. So I put derivatives acting on the curvature tensor to the 4th. Of course, there are more general terms you could write down with higher powers of the curvature, for example, or powers of other fields which enter, which I'm not talking about here. So this is a generic term, and every time you get 2 derivatives, you get a power of g to the G in the transformation from the string frame to the Einstein frame. So this power changes by a factor of g to the n over 2, and the scale outside the length scale power also changes. Now if I use this holographic dictionary, you see that this generic term has a power of n to the half minus n over 2. So every time you add derivatives, you go higher order in the alpha prime expansion, the low energy expansion of the string theory, and at the same time, that's interpreted in the Yang-Mills theory as terms which are higher order in inverse powers of n. So since it's the large n limit is the limit in which one can make contact between the Yang-Mills theory and the string theory, in the way I'm going to be talking about, you see that the higher order terms in alpha prime are interpreted as higher order powers of 1 over n. This is a limit where n is large, and I'm fixing the Yang-Mills coupling. This is not the limit which is usually talked about, which is the limit in which the 't Hooft coupling is fixed. 't Hooft coupling is not G, but it's G squared times n. It's G. So in the large n limit with fixed 't Hooft coupling, that's the limit which is relevant for making contact with gauge perturbation theory, but it's not the limit I'm going to be talking about. So let me now draw a picture. So the first correction to the Einstein-Hilbert term, if one's thinking of an effective action, will be an action in which you get 6 extra powers of derivatives, which means it's of order r to the 4th. And then I could go a higher, have more derivatives on r to the 4th. And the first few, which are drawn in mauve, are special in a way I'll describe in a minute. But of course, you can go on forever getting terms of higher and higher dimension. You could, of course, get terms of higher dimension by, for example, having more powers of the curvature. And then you would talk, these are the terms which would come up if, for example, you looked at 4-point function, 4 graviton scattering, or 5 graviton scattering, or 6 graviton scattering. Yes?
Do you have given tensor square terms, for instance? In addition to...
No, well, sorry, in the theories I'm talking about, I'm going to be talking about theories with maximal supersymmetry. And it turns out that for these, basically, because of the supersymmetry, the first term you get beyond the, the Einstein-Hilbert term, which is linear in curvature, is this r to the 4th term. Oh, sorry, I misunderstood the question. What?
Oh, the R is the Riemann tensor. Yeah, R is the Riemann tensor.
Sorry, yeah. There's a lot of notation I've suppressed here. So this is 4 Riemann curvatures contracted together. So they've got indices. And they're contracted in a way which is uniquely prescribed by supersymmetry. The first few, the ones in mauve, are ones of low dimension. These are dimensions up to 14. Each curvature has 2 derivatives. So d to the 6th r to the 4th has 14 derivatives. As soon as you get up to 16 derivatives, which are these terms, then you're no longer protected by supersymmetry. At least that's never been proved, but it's the intuitive assumption. And so we know much more about these terms of low order than we do when you go beyond there, simply because when you have low enough dimension, there's a protection by supersymmetry of the structure of the coefficients of these terms, which I'm going to review in a few minutes. I could, of course, have other kinds of interactions. There are other fields, as I mentioned, in the supersymmetric theory. So there's a field called G, another one called lambda, and such processes involving many of these other fields are interesting to look at. They're particularly interesting to look at because in string theory, there are many processes that violate a U1 symmetry, but that U1 symmetry cannot be violated in conventional supergravity. So there are processes in string theory which have no correspondence in supergravity. And then, of course, one could make contact with 11 dimensions because the whole structure of string theory can be related to M theory, or 11-dimensional supergravity. One could compactify on a torus, for example, and then one can say some very precise things about the theory in lower dimensions, which I'm not going to talk about in this talk. But what happens when you compactify on a torus is that the duality groups get larger and larger as you go compactify in larger and larger dimension tori. So the one I'm going to be talking about in this talk will be entirely SL2, which is the 10-dimensional duality group of the type 2B theory. But as you go down by compactifying on a torus to lower dimensions, there's some absolutely fascinating properties of the amplitude that are revealed, which are determined by these higher rank duality groups. So for example, in 4 dimensions, the string theory you get is related at low energies to n equals 8 supergravity, which is a much studied theory, at least in the past. And then finally on this slide, there is of course this link, which I will be talking about, between this string theory in 10 dimensions, but in a special background, to maximally symmetric n equals 4 Yang-Mills. Right, so I'm going to now concentrate entirely on the 10-dimensional type 2b theory, the one with maximal supersymmetry. So in that theory, there is one complex parameter, scalar parameter, which is called tau in this talk. So it's got a real part and an imaginary part. The imaginary part I've already mentioned is the dilaton factor, the 1 over e to the minus phi, which will often appear in this talk as 1 over the coupling constant. This scalar field parameterizes a coset space. That's true of all the supergravity theories, that the scalar fields lie in a coset space, which in this case is SL2R, modded out by U1. It's actually this U1, which is the R symmetry, that gets violated in the interactions I just described on the previous transparency, the U1 violating interactions. This tau you can think of as a coordinate on a torus. It's subject to discrete identifications due to large diffeomorphisms of the torus. And so the symmetry is broken. You have to mod out by this coset space by discretely identifying the torus under Dane twists, for example. And so SL2Z is the duality group. So we expect our amplitudes to be invariant under SL2Z transformations, which are characterized by this transformation of tau, where A, B, C, and D are integers with determinant 1. And then the question that I'll be asking is, knowing that the amplitudes are invariant under both maximal supersymmetry and this SL2Z, how much can one say about the structure of this low-energy expansion? So I'm going to start by talking about the amplitude. And the simplest amplitude that one can discuss is the 4-graviton amplitude, which has been discussed a great deal both in string theory and in supergravity, the corresponding supergravity. And the supersymmetry of the theory allows you to factor out this coefficient r to the 4th to all orders in well, in fact, it's an exact statement that the amplitude can be written as r to the 4th times a scalar function of the Mandelstam invariance, ST and U, where r here means you take the linearized curvature, which means you have a polarization tensor for each graviton and multiplied by 2 momenta. And then there are 4 indices on the curvature tensor. So knowing about T tells you about the amplitude. So T is a symmetric function of these Mandelstam invariants. And I'm going to assume, for the purpose of this talk, something which in fact is a correct assumption up to the order in which I'm going to be describing the theory, which is that T is an analytic function of ST and U. And it's a symmetric function. And if you impose the fact that S plus T plus U is 0, you discover that such a function is a power series in S squared plus T squared plus U squared and S cubed plus T cubed plus U cubed. In other words, it's a power series in sigma 2 and sigma 3. And that notation will come back a great deal in the next few transparencies. So just remember, sigma 2 is quadratic in the Mandelstam invariance and sigma 3 is cubic. Of course, the theory has thresholds, non-analytic behavior, absolutely crucial, of course, because that's where the physics sits. But those thresholds will not enter the discussion up to, in fact, up to the order in the low-energy expansion, which is of interest to us because it only involves the BPS terms. So this statement is then the statement that the scalar function T has an expansion in powers of sigma 2 and sigma 3 with coefficients which depend on this tau, the parameter tau, the modulus. It's these coefficients that have to, so because the amplitude has to be invariant under SL2Z, these coefficients are SL2Z invariant functions or modular functions. Here there's a single scalar field tau. In the other, the the theories you get after compactification, the ones I mentioned earlier, there were higher rank duality groups, and there were many more scalar fields or moduli. And so for the higher rank groups, then the corresponding coefficients have to be invariant under the higher rank duality symmetries. But I won't be talking about those here.
So what is P and Q then?
Sorry, this is a sum over P and Q. They're integers. I'm just expanding in powers of S, T, and U, the Mandelstam invariance, but imposing the condition that T is a symmetric function, and also that S plus T plus U vanishes. So,
Kind of crossing symmetry that you're imposing?
that imposes crossing symmetry, which is sort of almost trivial for these terms, because it's just a statement that it's symmetric.
These are on shell.
Well, these are on-shell, these are amplitudes. Yeah, I'm only talking about amplitudes. Can you shout?
Is it just a homomorphic function? Can't it depend on tau bar?
Yes, so in this notation, there seems to be a controversy when I talk to people about whether saying it's a function of tau automatically means it's a function of tau bar or not. Of course, if it does, I have to say this is not homomorphic. Then it's a function of tau and tau bar. Maybe it would be clearer if I'd written tau bar. It's just, yeah. So this is the complete expansion. This function is an interesting function because it's invariant under SL2, but in particular, it should contain within it string perturbation theory results. And that string perturbation theory is what you see at small coupling, or as tau2 goes to infinity, which is the cusp in SL2Z in the moduli space. So there is a boundary. There's boundary information that you can get at by doing actual string calculations at tree level, 1 loop, 2 loops, and so on. And that information is absolutely, I mean, there's not a huge amount of such information because no one's ever constructed a string theory beyond 3 loops in any very explicit form. But up to 3 loops, there's a lot of information that one can compare with, that one can either use as input, or one can, if one understood what these functions were, one could check that they might be correct, which is what I'm going to do now. But let me first review, just for the sake of completeness, the structure of these, of a couple of orders in perturbation theory. So at tree level is of order 1 over g squared in string theory. So this should be straight R, actually. Curly R doesn't mean it's the same as straight R. And then the function t is t naught is the genus 0. So I've represented the fact that this is this is the string theory amplitude you get with a spherical world sheet, and these are the 4 particles attached with vertex operators to a spherical world sheet. There is a very well-known expression for this. This is the supersymmetric version, if you like, of the original amplitude that Virasoro wrote down in the late 60s. It's just the ratio of 3 gamma functions, product of 3 gamma functions divided by product of 3 gamma functions. That can easily be rewritten using elementary features of the gamma function as an exponential of a series of terms with powers, higher and higher powers of S, T, and U. And so the low energy expansion can be done explicitly to all orders rather straightforwardly. And I've written down some of the first few terms just to show you how these correspond to the terms I was talking about before. So the lowest order term, sigma 3 is S cubed plus t cubed plus U cubed, but that's actually STU. It's proportional. It's 3 times S times T times U. And then that gets multiplied by R to the 4th. And this is actually a rather economic way of writing the supergravity answer. So this is what you get from Einstein's theory. The next term is the first correction, the R to the 4th term that I talked about before. And here you see its coefficient is a Riemann zeta value, zeta 3. The term after that has 4 derivatives on R to the 4th, and it's a Riemann zeta value 5. And then you get the 6th R to the 4th, which has Riemann zeta value 3 squared, and so on. And you can go on forever, of course. But it's these first 3 terms, which are the ones which I stressed before, are the ones which we expect to be protected. And now this explicit calculation shows that all the coefficients, well, not only are they known, but they have a certain feature. In fact, all the coefficients in the whole expansion are powers of odd zeta values. This turns out to be rather interesting, rather trivial for this function, but it's an interesting aspect of the perturbation expansion, or at least at tree level. This generalizes, in a way I won't show you, but it generalizes if you look at n-particle scattering, and then you again get zeta values, but this time they're multiple zeta values, which you may not know much about, but these are obvious generalizations of the Riemann zeta value. People in recent years have studied in great detail the expansions of the endpoint functions, both in closed string theory, which is what this is, and in open string theory. And you get these fascinating objects which mathematicians are very interested in. So there's a whole area of interplay between the mathematics community and the physics community involving properties of multiple zeta values, which are deeply connected to multiple polylogs. And of course, those arise in quantum field theory as well. So there's a sort of symbiosis between the communities who are studying higher loop quantum field theory and aspects of string theory and mathematics. Yes?
Is there any reason why you don't get R to the 6?
Well, I'm looking at the 4-point function. So, yes. So for the endpoint functions, you'll get higher and higher powers of that. Genus 1, I don't want to spend too much time doing this, so I will skip through this. But let me just say, genus 1, this is the one-loop string amplitude. That's more difficult to expand, of course, because now what you have to do is, the amplitude is, the world sheet is a torus. What you do is attach vertex operators on the torus and integrate over the positions of the vertex operators. And that gives you a function at fixed tau. So the torus is parameterized by a complex structure tau, not to be confused with the tau I had before, which was the coupling constant. So for this slide only, tau means something different. This tells you about the shape of the torus, and you have to integrate over it. And this function b is what you get from the product of 4 vertex operators integrated over their position z on the torus. And g is the Green's function on the torus. So this is a fairly complicated but well-known expression. But to expand it in powers of momenta, or st and u, you have to expand in powers of ki dot kj. So that's quite difficult. And there's a whole art to doing that, which I'm not going to describe. But that brings down powers of the Green's function, and then you have to integrate some power of the Green's function to get the function b, and then you have to integrate the function b over tau. I'm skipping through this because it isn't relevant directly to what I'm going to say later, but let me simply say that having done that, you get an expansion in powers of st and u, just like at tree level, again with coefficients which are powers of Riemann zeta, of odd Riemann zeta values. But at this point, you have to worry about whether there are thresholds, because this is a loop amplitude, and just like in quantum field theory, loop amplitudes give you non-analytic branch points in the Mandelstam invariance. But actually, up to the order I'm talking about, these can be separated, and one can talk about the analytic part directly. So I'm now going to summarize what's known beyond perturbation. So those are 2 perturbative terms. A lot is also now known about the 2-loop amplitude, and a minuscule amount of information is known about 3 loops, thanks largely to Nathan's method of doing the calculations and his students doing them. So that's the boundary data. That's the perturbative data. If you want to look at the non-perturbative sector, you really have to understand aspects of these functions as I was talking about. So the amplitude, I'm just reminding you that the amplitude can be written as r to the 4th times a scalar function. The scalar function is expanded with coefficient functions which are SL2Z invariants. We want to determine these, and I haven't got time to tell you how they're determined, but I will tell you what they are up to the order we know them. But they can be determined both by using supersymmetry and also by some detective work using the fact that this theory is related in 11 dimensions to 11-dimensional supergravity. So what the result of knowing that is that these coefficients, to a certain extent, and the low-order ones are known. By low order, I mean, for example, when P and Q are both 0, that's the coefficient of the R to the 4th term. There's no momentum, there's no 0 powers of S, T, and U multiplying R to the 4th. That coefficient satisfies a Laplace eigenvalue equation where the Laplacian is the Laplacian in the tau plane, the hyperbolic plane. This hyperbolic Laplacian. And this equation is a much studied equation in which actually when we first did this we had no idea what we were doing, but it turns out this is a much studied equation and mathematicians love it. The eigenvalue is crucial in a way I'll tell you in a minute. The d to the 4th r to the 4th satisfies a similar equation but with a different eigenvalue. The solutions of these equations are Eisenstein series, and I'm not sure that you will all know what an Eisenstein series is. These are non-holomorphic Eisenstein series, not to be confused with the ones which are perhaps more familiar, which are holomorphic. But I'll just show you what these are. So the definition is very straightforward. There's a parameter S in the definition, and it's a double sum over two oops, I mistyped. That should say n. It's n plus n tau to the power 2s in the denominator, modulus, and a tau 2 to the s in the numerator. And this thing, you can easily see by playing around with it, is SL2Z invariant. So this is a modular function. In fact, this can be generalized to any of the higher rank groups which I mentioned earlier that you get in the compactified theory. And it is a solution, indeed, of precisely the kind of eigenvalue equation that I have mentioned before. So and it's, in fact, the unique solution, given a boundary condition that E should not diverge when tau 2 goes to infinity, weak coupling, it shouldn't be worse than power behaved. And since we know that string theory, the lowest order term, the leading term at weak coupling is the tree level term, we know that it's power behaved at worst. So there's a unique solution to this equation. S times S minus 1 was, if you remember on the previous transparency, I had 3 quarters and 15 quarters. So those are the cases where S is 3 halves or 5 halves, which will come back in a minute. But let me first say that in general, this Eisenstein series has a beautiful Fourier expansion. It has a Fourier expansion with a 0 mode and then a sum of, I'm sorry, there's a misprint. That should say tau 1, not tau 2. There's a function of tau 2 multiplying a cosine, or an e to the I, 2 pi I k tau 1. So the 0 mode is very simple. The 0 mode has 2 power behaved terms, 2 and only 2. And the non-zero mode is proportional to a Bessel function of tau 2 with a particular arithmetic coefficient, which is a divisor sum, which is, again, I've forgotten, it's a function of k. This should say subscript 2s minus 1, a function of k. So this is some well-defined coefficient multiplying a Bessel function. But the Bessel function has the property that in the perturbative limit, or in the small weak coupling limit, it decreases like an exponential. So this is like an instanton, because remember tau 2 is 1 over the coupling constant. So since tau 2 is 1 over the coupling constant, this looks like e to the minus some integer over 2 pi times an integer over the coupling constant. So this looks like an instanton. So there's a sum over an infinite set of instantons, this zero mode has two power behaved terms, so this looks like perturbation theory. That's why I put the word perturbative here. So this function contains both perturbative terms in the string language and non-perturbative terms. So you can compare the coefficients with what we know is true in string theory. See, this was derived from supersymmetry and dualities, but there was no string calculation involved. But when you can compare the coefficients, say, this is the r to the fourth term, you have to go back to the string frame to compare it with string theory, and you find the first power behaved term is a tree level term, the second one is a one loop term, and then there are an infinite set of instantonic terms, which would be identified with what are called d-instantons in string theory. So you see that here is a sort of prediction that at this order, there is a non-renormalization beyond one loop. You only get tree level in one loop with very specific coefficients. Similarly, for the next term, there are two power behaved terms. This is the r to the fourth term, the 1, 0 coefficient. And that's got the Eisenstein series E5 halves. Remember, the eigenvalue was 5 halves in that case. And here there's a tree level term, and this time there's no one loop term. The coefficient of the genus 1 term vanishes. This is d to the fourth, r to the fourth. And indeed, that's true. If you calculate one loop string theory, you find the coefficient of this term is 0. But then there's a coefficient of a two loop term, which has also been extracted. But there's nothing beyond it. So in both cases, there are non-renormalization statements for the perturbative pieces beyond one loop or beyond two loops. So these are very simple functions which contain a huge amount of information. When I say a huge amount, they in particular contain these coefficients of these divisor sums, which are the coefficients of the instanton terms, and those are very striking statements about the d-instanton measure. The next term, and the last one I'm going to talk about, is of order d to the sixth r to the fourth, and that's the E01 coefficient, and that is a richer function. It's not an Eisenstein series, but it's a generalization of an Eisenstein series, which satisfies a Laplace eigenvalue equation with an inhomogeneous term on the right-hand side, where that term is itself the square of the coefficient of the r to the fourth term. And one can motivate this directly from supersymmetry, or you can motivate it by duality in a way which I'm not going to describe, but is mentioned here. So you can solve this equation as well. And this equation has some weird and wonderful features, which I'm not going to describe in detail, but let me simply say that the zero mode bit, the bit which has no net d-instanton number, now has, instead of having two terms, has four terms, genus 0 to genus 3, with coefficients which are very precisely defined by the equation. And it also has a sum of an infinite set of instanton, anti-instanton terms with instanton number 0. So this is all in the zero mode, and all these coefficients can be calculated in string perturbation theory, and they all agree. So there's a complete agreement in some detail with string loop calculations. So that's a very brief summary of where we are. Have I got 5 more minutes? Good. This is a brief summary of where we are in part of the discussion of the string theory scattering amplitudes in higher dimensions. Let me now turn to the second part of the talk, which was always going to be sketchy and is now going to be very sketchy, which is how to understand some of these features, starting with the Yang-Mills theory in 4 dimensions and using holography. And this is very much following earlier work by a large numbers of people who've been studying this in recent years, and I and Kong-Kao Wen have joined in with a group that were part of that earlier work. So the idea is to look at the correlation functions in 4 dimensions, and in particular take the most straightforward correlation function, which is the correlation of a four-point function with the 20 prime operators. These are gauge invariant bilinears of the scalar field in Yang-Mills, in n equals 4 Yang-Mills theory. And these are the operators which are dual to the graviton, which are supposed to connect. They're dual in the holographic sense with the graviton. So the four superconformal primary correlation function should be related to the 4 graviton amplitude in some limit. So the way that this works is you start with something which has been studied by now for the last 15 years or so, the so-called Pestun partition function, which is a partition function for the theory on a sphere, S4, which can be calculated exactly. So this is a functional integral, but this particular one is localizable, which means you can reduce the functional integral to an ordinary integral over a scalar field, a set of scalar fields, and therefore you can actually make exact calculations for it, for the partition function. So Pestun's partition function, the one that we're talking about, is a function for a mass-deformed version of the n equals 4 Yang-Mills theory. It's the theory often known as the n equals 2 star theory. But we're actually interested in the n equals 4 theory, so we want to take the massless limit. But we don't want the partition function, because that's rather trivial in the massless limit. We want the correlation function. And I should have, in a minute you'll see some names of the people who did this. But it was realized very cleverly that if you take certain derivatives of the log of the partition function, and then take the massless limit after taking the derivatives, you get a correlation function which is itself localizable. So once the aim is to calculate something localizable, because then you can do the exact calculation. So Z here is an exactly calculable partition function, Pestun's partition function. In fact, you can write it as a product of a classical piece, a one-loop piece. It's one loop exact, and then it's got an instantonic piece, which is actually something discussed by Nekrasov earlier. So the people who did this calculation were these ones, Binder, Chester, Pufu, and Wang, who they looked particularly at the perturbative factors. And there are many technical issues. I can't possibly go into this. It would take more than a whole lecture to talk about it. But there are many technical issues that you need to overcome in order to come up with the results. But what they discovered was that if you take the large n limit, and now you take the 't Hooft limit, then you find that in the large n limit, this partition function that can be expanded in powers of 1 over lambda. So you expand both in n, at large n, and 1 over lambda, and you discover that the leading term is the supergravity answer. It's just a constant times n squared. It's independent of lambda, because supergravity doesn't know anything about lambda. And then the next term is a coefficient which should be, so this is, on the left, I've written the answer I had earlier from string theory. What these people found were these two terms here with precisely the right coefficient. I've left off the coefficients here, but they found the right coefficients to correspond to those terms. And the instantons were neglected because in this particular limit, when n goes to infinity with fixed lambda, the instantons are suppressed by powers of e to the minus n over lambda. So they didn't consider the instantons, but they did get these power-behaved terms correctly. So the work that I've been doing then recently was to try and get the instanton piece correct. So what we expect to get is what I wrote earlier. We expect to get, we're now going to keep G fixed. So instead of keeping lambda fixed, we're going to keep G fixed, which means lambda will be, by definition, it will go to infinity. But if you keep G fixed, you've got a chance of preserving the SL2Z invariance, because the SL2Z invariance relates the instanton terms the non-perturbative terms to the perturbative terms. So you expect to get this, which translated into the Yang-Mills notation involved these two power-behaved terms, and then these Bessel functions, which were the instanton terms. At small, if you let the Yang-Mills coupling be small, this becomes the exponential approximation to the Bessel function. And in this language, in the Yang-Mills language, tau, which I call tau 1 plus I tau 2, is simply theta, the theta angle, plus I over g squared, basically. And you get instantonic terms. And I think, in view of the time, and in view of the fact that I've got some rather complicated formulae, let me just simply say that if you do the calculation and include the instantons, which is a very tricky calculation, as it turns out, then indeed you reproduce precisely and exactly this infinite sum. And that, it's rather, it's technically complicated, but nevertheless it looks very interesting. So let me just flash through this and simply say that you can pick out the instantons. It's complicated, and it would be nice to find some simpler systematics instead of having to pick out each instanton separately and show what the general instanton contribution is. Somehow the whole package should come together. So let me just finish with a few comments. So this is just to say what we've done. We reproduced, or this method reproduces the flat space, the expected flat space answer up to this order, d to the fourth r to the fourth. There's one further order, d to the sixth r to the fourth, which satisfies that inhomogeneous Laplace equation, which is more tricky and which is not reproduced by this particular calculation I just mentioned, but we know how to get it. So one of the problems with this method, remember with this procedure, I don't know if I stressed that. Let me just quickly stress it. This procedure using this correlation function, it actually gives integrated. It doesn't give you the correlation function itself, it gives you the integral of the correlation function. So it loses some information which one would like to have. But we know that there are alternative definitions of the correlation function. So instead of taking 2 derivatives with respect to mass, you could take 4 derivatives with respect to mass, and you get a slightly different, well, a qualitatively different version of the correlation function, which will resolve some of the ambiguities that you have in the original one. I thought I would show you, so this is going back to the correlation function I had before, which is 2 derivatives on log z and a tau derivative and a tau bar derivative. I said that the leading term was supergravity. The next term was this E3 halves of order root n. The next term is 1 over root n times an E5 halves. We also have evidence, so going beyond there is very difficult, going beyond there analytically. But if you are fairly wizard with Mathematica, which I'm not, but my co-authors are, you can do numerical investigations, and you end up with a conjectured expression, I mean, more or less shown up to the order shown, but this seems to go on forever. For every order in 1 over n, the coefficients are sums of half-integer Eisenstein series with rational coefficients, well, apart from some powers of pi. So there's some fascinating all-orders expansion for this thing, which mathematically looks very interesting. What the interpretation is in string theory, I don't know. And then finally, let me just say that there's some obvious questions about how you could make other connections with string theory using this technique, in particular these other processes which were U1 violating, or the processes that you get when you compactify on a torus. So I think I'll stop there. Thank you.
Could you just give a sketch of the idea of how the constraints of nonlinear supersymmetry work? How do we impose just nonlinear supersymmetry? Forgetting about string theory, M theory, just nonlinear supersymmetry, what would we learn about the amplitude and how would it go in practice?
Well, I mean, the only way I know of trying to do that is using the component supersymmetry, which is very complicated. So I don't know that one would ever be able to do it beyond some particular processes. But if you, the point is, roughly speaking, that as the supersymmetry transformation, take some effective interaction. Supersymmetry related to another effective interaction, which will have a different, well, a different set of fields, but it will differ by, it will have different U1 charge, basically. And then you do another supersymmetry transformation, takes it back down again, and you get a Laplace equation. I don't know how one would ever do it beyond, I mean, there's no off-shell superspace formulation of the theory. There's no on-shell superspace formulation which in any sensible way gives all the interactions you want to describe. So I only know a method which uses the component formalism, the components, which satisfy very complicated supersymmetry transformations. And then if you just work very hard, but there is an alternative method that uses sort of the Ward identities, which is a much more recent.
So let me understand something. So the full amplitude, of course, the various 2-to-2 scattering processes are all related by supersymmetry, right? Are these the Ward identities?
No.
Or no, more?
No, you need more than that. So for example, let me give the example. There are, actually, I deleted a lot of transparencies, luckily, yesterday, but amongst them were the ones which were giving an indication of how supersymmetry, in fact, relates things. But but for example, there's this term which has r to the fourth, but there are many other terms which involve higher powers of fields, which are all related by supersymmetry. Actually, by supersymmetry. So I could draw. So you can package the physical fields into a scalar superfield, which satisfies some sort of chirality constraint. So it's a function of theta, but not theta bar, and it satisfies some constraints. It satisfies an on-shell constraint. This is sometimes called a Howell-West superfield, but it contains, as a first term, it contains tau, and then it contains theta times the dilatino, which is a spin-a-half field, and then it contains theta squared. I'm leaving all the indices off, of course, times the third rank field strength of the Ramond and Never-Schwarz field. It's a complex combination, and then it contains a covariant derivative on the gravitino, and then theta to the fourth contains r plus actually a derivative on the 5 form, and so on, until you get to the last term is theta to the 8th. It terminates at theta to the 8th, times 4 derivatives on tau bar, the complex conjugate of tau. So once you've written this down, this is a function of theta. Theta has 16 components. You can imagine writing a supersymmetric effective Lagrangian by integrating over 16 thetas and take some function of phi. Actually, this tau, you want to write as the background tau plus a fluctuation. So I'm going to write this as delta tau, and then this is phi plus tau naught. So I've written tau equals tau naught plus delta tau. So you have to, there's a vacuum value for tau. So now when you integrate this over 16 thetas, you get a large set of terms. You pick out all the terms you can get. Imagine you do an expansion of this, starting with, well, it will have a lot of terms in it, but for example, there's a term which has 4 thetas, 4 derivatives of f with respect to tau naught, evaluated at tau naught, plus, I'm sorry, I'm saying this one. So there's a term where you pick out r by taking 4 derivatives of this, and you get 16 thetas with an r to the 4th. Okay? And then there's another term which would have 16 thetas, and then you take 12 derivatives of f, 16 derivatives of f, with a lambda to the 16, plus a lot of other terms. So you pick out all the terms which are of order, which have 16 powers of theta, and they're all related by supersymmetry because this is a superfield, and supersymmetry acts in a way which relates all the components. So you did ask for a hint as to how things. So that's a hint that you pick up a lot of terms.
So I'm not from this field, but I've heard things like double copy that you can use to compute. So it's about the second part, the ADS-CFT duality. Does it shed any light on this double copy formalism?
Well, does it shed any? Not that I know of. I mean, it seems to be a rather different language.
How, if you change the derivatives of the log of the partition function, how this can resolve the ambiguity? I can see that. Because the derivative will fall down some fields in the expectation value, then this is an integrated correlator.
Yeah.
But how can you resolve the ambiguity of the fact that you are integrating a correlator?
If you can find another definition by taking other derivatives on the log of the partition function.
But the fields that are going to fall is not the same, and the integral will be the same, right? No.
Yeah, but you won't get the same. So, for example, in the this object here, which is the one which we were calculating, only has half integer powers of 1 over n. So it doesn't contain within it the term which had, which I call d to the 6th r to the 4th, which is s cubed plus t cubed plus u cubed times r to the 4th. That term behaves like 1 over n instead of having a half integer power. So that isn't contained here, and the reason it's not contained here is because this particular correlation function gives you an integration measure which kills that term. It kills terms which are odd in Mandelstam invariance. So, but this guy here contains that term. So you get a different set of terms depending on which of these correlation functions you look at, and
so this M is supposed to have indices, right?
which M?
This mass.
Indices.
The mass term.
It's a parameter.
It's just a parameter.
Sorry, I've just lost the. It's a scalar. It's just a parameter. It's a mass parameter. Maybe I don't. What? No. Yes. Yeah.
How can you get the 20 scalar field if you're making
what
derivative?
what you do is you start with the theory which is not the n equals 4 theory. It's the mass deformed n equals 4 theory.
And there's this mij coupled with some scalars, right? Giving mass to I per multiplied. This n equals to a star.
Yeah, but there's an overall mass scale for the n equals 2 star case, which.
Okay, I don't understand. Good.
Right, and if you take the massless limit, you get back to the n equals 4 theory. So there's a single parameter that when you set it equal to 0, it gives you the n equals 4 theory. And these correlation functions involve taking derivatives with respect to that mass scale.
Okay.
So let's thank Michael again.
Oh, I better get rid of this.
After Marcel Fisher, I think we're going to take you to the airport.
Oh,
After he finishes.
is he next?
Yeah.
I see. Okay.
He's right, he's at 4, right?
Yeah, I got plenty of time.